All right, everyone, let's get started. So as I mentioned last week, I don't have a new lecture for you today. I'm planning just to do some review for the exam. The exam is open right now. You can take it anytime this week up until 11:59 p.m. on Friday. Once you start taking it, you have 75 minutes to complete it. And if you have any questions or you see anything strange, let us know. Email us. How is everything going in lab? Any issues? Yes.
I don't think anybody realized that they have to build an assembler program for binary to decimal.
There's two tests that we want you to do for your CPU. The first one is in a program that's in the lecture slides that we give you.
Yeah.
And it's a really simple program that doesn't really do anything useful. It just tests every instruction. Mm-hmm. The second program is the binary to decimal conversion program. The purpose of that is to test your CPU, but it's not a great test because it's probably not going to require all of the instructions in your instruction set. The primary purpose of that program is to have it something you can demo, basically something running on the board that does something interesting, meaningful, right? So the objective is once you deploy all your hardware and your software, you have the DE2 board, you can flip the switches, and it should show the decimal number on the hex displays. You've already built your 7-segment decoders, so you'll be using those in hardware. And then in the next lab, we'll be using the binary to base 10 converter to basically build a calculator. Do a square root calculation rather, where you put a number on the switches, it calculates the square root, and then puts the decimal number on the switches. The way that works is that your switches, there's 18 switches, so that's going to allow you to put an integer from 0 to 2 to the 18th power minus 1, which is 262,000, right? Now that's only a 6-digit number, so even if you move all the switches up, you're not actually going to be able to use the leftmost 2 digits on the hex displays, because remember you got 8 hex displays, 8 hex digits. But that's okay because we will be using all 8 digits in the next lab, okay? Remember though that the hex digits are not individually addressable. You can't write code that will send a digit to a specific hex display or 7-segment display. All you can do is use the CSSRW instruction to transfer a 32-bit value from a register from a general purpose register into the output register that goes to the hex decoders, right? Meaning that if you want to put specific digits in specific places, you need to do some bit twiddling, right? You need to be able to maneuver each of the 4-bit decimal values into the correct position within the 32-bit value that you will then output to the hex displays. You guys with me? Okay, so there's a little bit of bit manipulation in there. I didn't talk about that much last lecture, but the way the algorithm works is that it strips off each digit from right to left, right? So keep that in mind. You're writing this iterative algorithm that's extracting base 10 digits from the input value from least significant to most significant. So every time you extract one of those digits, it has to go in first it'll go in the rightmost 4 bits, and then the next 4 bits moving to the left, and the next 4 bits. In other words, bits 3 down to 0 is the first digit you extract, right? You're going to put the first digit you extract into bits 3 down to 0 into some register, right? Some output register, right? Then the next digit will go in 7 down to 4, and then 11 down to 12, and so on, right? And once you've put all those digits in there, then the final thing your program will do is issue the CSSRW instruction, which will then light up the hex displays. And then because we don't have any branch or jump instructions, your program is just going to be running continuously in an infinite loop, because once your program counter gets to the last addressable address, which is 4095, if you're using a 12-bit PC value, then the odometer is going to flip back to 0 and it's going to go back to 0. So your program will naturally run in an infinite loop, which is nice because that will create essentially an embedded program where when you switch any of the switches on the board, it will update the hex displays seemingly instantaneously, even though in reality it's taking, I don't know, 100 clock cycles or so, right? But you won't notice that because it's 100 cycles on a 50 megahertz clock, so it's 100 divided by 50 millionth of a second, right? But it'll look like every time you flip a switch, it'll instantly update the hex displays, right? And so that's the way it should work, and that's what hopefully you'll be able to demo. So the point of this program is we're not trying to give you this big programming workload because this is supposed to be a hardware class, but it's to actually achieve something tangible, right? Where you can actually run something on the board and demo it and say that you designed the software and the hardware for basically a calculator, right? Essentially, like a handheld calculator sort of thing. Okay, so that's how that works. Any other questions about that? Does that make sense? I had a few questions over email about how the algorithm works. So the idea there is that we're just using fixed point to implement. So we're doing a divide by a constant. We're dividing by 10. And so anytime you divide by a constant, you can just multiply it by the inverse of that constant, right? And so the value you're multiplying against is 0.1 or 1/10. So in fixed point, 1/10 is just the range of the 32-bit number divided by 10. So it's 2 to the 32nd power divided by 10, which is roughly 429 million, right? Something like that, right? So then you multiply that, and that'll give you, that'll essentially take the input value and knock off the rightmost base 10 digit. But then you have to recover that digit that you knocked off so you can stick it in your register for output. And so to do that, you take the fractional part of the product and multiply that by 10. Now I figured out today, and I think I had forgotten this, but 2 to the 32nd power divided by 10 is not it's not evenly divisible by 10, right? So you end up with a number that's 429 million something, and then there's a 0.6 at the end. If you round that number down when you put it inside your constant, then it actually breaks the algorithm. At least for the example I did. I was going through an example with someone today, and I realized that I rounded it down, and I took 27 was the input value, and I multiplied it by 0.1, and then I multiplied the fractional part of the product by 10, and I didn't get what I expected. It didn't work out. It came out to be I think 26 or something like that, right? So make sure you round up whatever 2 to the 32nd power divided by 10 is. Round that up, right, when you put that in as your constant. Okay. Okay. Any other questions about the lab? Yeah, we realize that it's a big jump in difficulty, but I've been teaching this class for a long time, since the 90s. And I've never found another way to sort of ease into the CPU project. I tried, at one point we had a thing where we said, design the fetch stage, just the fetch stage by itself. But it was really confusing as to what you were supposed to expect if you just have a fetch stage, right? And it didn't go over very well. And then we said, well, how about just a few instructions, right? Like just add and subtract. But the problem with that is if you have no I-type instructions, you can't initialize registers, right? There's no way to set up the 0.1 and the 10 inside of a register. So that didn't work out so well. So I think this is it's a big jump in difficulty, but there's no better way, I found at least, to get into the CPU design. And then of course, once you have your base CPU design, then going to the next lab where we had branches and jumps is actually a lot easier because you've got a nicer starting point. So I think this lab might actually be the hardest one, just because of the, you have to go from nothing and get a CPU. Yes?
Do you think you can give us an extra week for this lab?
Possibly, but the schedule is pretty tight. I've got everything planned out, and in the past when I've done that, when we let deadlines slip, it ends up basically we don't finish the CPU or don't finish the, well, we only have one more lab. So, of course, there's the graduate lab for the grad students. But I'll have to look at the schedule and see how we can work that out.
Maybe we can keep same schedule, just omit that part when you lose 7.5 points per day.
Well, we already have that. Yeah, I already have a late policy. It's 7.5% per day, capped at 30%. So.
Just move it to like the next lab day, since we have from Sunday to like Thursday, then we wouldn't be working anyways.
Yeah, that should be okay. Yeah, I can do that. Okay, so don't forget to take the final exam. And if you see anything weird, let me know. Sometimes there's typos in those things, or there's a bug. That's one of the issues with Moodle, is that we write the exam using a language called GIFT, and then which is like a weird hybrid of a proprietary language and HTML, and then you load it in, and sometimes there's some translation problems. Okay, so today I'm just going to review for the exam. I found some old exam questions that I've asked, so I just kind of threw them into this document. I think I've got 16 of them. So the first question is, identify any problems. I don't know how well, you guys can see that in the back. Let's zoom in a bit more. Hello? Are we hung? Oh, we're hung. Okay, hold on a second, sorry. There we go. Okay, identify any problems with the module below. Anyone see any issues there? Yes.
Well, I can see one, two, three. I can see three issues just looking off right at the bat.
Okay.
So for starters, you have the sign statements in an always com.
Okay, that's right.
Two, you have your output. Your output logic C is 4 bits, and your input logic's 3 bits. So you're just adding stuff to a C. You can add stuff to C, but it's just weird. And then B, and then the if statement. B. If you look at the if statement for B, it's not logical. It's just it's like 2, so you're just always going to be true. If this was C, but
yeah. So B is
multiple bits.
3 bits and used in an if statement, if condition. Yep, I think that's right. Although I think.
You may have forgot logic.
Oh, you're right. Yep, I forgot logic too. Yep. So the logic, actually, you don't have to put logic in for the inputs, although I always do. You can, but it's optional. But you need to put it. You do need it for the output. So that's actually okay. But I agree, though. You should. The way I code is I put logic on inputs and outputs. The if statement, I think that would compile. I would assume that Verilog or System Verilog would treat that like if B is 0, 0, 0, then it would be false, and anything non-zero would be true. But I've never actually tried it, so I don't know if I would have to try it and see how it works. Yes.
Wouldn't the width, or like if you add two numbers together and then you have a 1,
So this is a bitwise and. So you would get, in this case, A and B, you would get a 3-bit result there. Same way, it works the same way actually in C and Java too. If you use a single ampersand, it's a bitwise operation. Okay, great. Next one, number 2. To what value will the system Verilog code set to signal B when A is 10111? So this is a bit twiddling operation. So, yes?
1100.
1100, okay, is that right? A0, oh wait a minute, oh yeah, A0 is 1, A1 is 1, right? And then 2 copies of A bit 2, which is 0, 1, 2, 0, 0. That's right, yeah, great. Well, that's easy. Write a system Verilog module named parity. It receives 3 1-bit inputs A, B, and C. It produces a 1-bit output Y that is true if an odd number of the inputs are true. So we have module parity, inputs logic A, B, C, outputs logic Y, and module. Okay, and then how would we implement this? Yes.
XOR of all of them?
Yes, yeah, that'll work. So we can just do a simple. We just do a sine Y equals A XOR B XOR C. That should do it. Okay. 4. Okay, this one gets a little bit more complex because we get into the microarchitecture. Consider the design of a 3-stage pipeline CPU design shown below. I just created this version of the design. This picture takes all of the 3, I think, separate pictures I gave you before and consolidates them all into one unified block diagram. So we've got the instruction memory, so the fetch stuff is going on over here. We've got the register file, ALU, control unit, and most of this stuff is registers and muxes. So I think that's complete, but it's a new design, a new picture. So write a system Verilog snippet to implement the Sine extend block. So back when we were doing MIPS, the Sine extend block is the way that you take an immediate value that's less than 32 bits and you plug it into you route it into a 32-bit ALU. Yes?
The concatenation of the last, of the most significant bit.
Right, yeah, so you can, well, the first problem here is we need to name that wire. I don't have a name on the output. Also, I forgot the arrow there going in the mux, but yeah, we don't, so I'm just going to call that, let's say a sine, I'll just say SE, sine extend, equals. Okay, now how do we sine extend this? Well, the input is going to be instruction _EX, and the sine bit for that is, well, in this case, well, the immediate field is 31 down to 20. So the sine bit of the immediate field is 31. Now this is not using the instruction decoder that Charles proposed in the lab sheet, where you would actually have a name for this signal that would be called IMM12, right? I'm just, in this case, I'm just assuming that this is, I'm gonna rip these bits right out of the instruction directly. Okay, so instruction EX31 is my sine bit. And then, so I would have to put this in curly braces. And anyone remember how you would sine extend that?
There are 11.
Well, there's 12 bits. There's 12 bits coming in. We have 32 bits going out. So we're missing 20 bits, right? We need to pick up 20 bits from somewhere. So with sine extending, you're going to take the sine bit and replicate that 20 times, and then prepend it to the immediate, right? So we can just put 20 like this. Okay, so putting 20 with the double curly braces will copy that 20 times, and then that'll give us 20 bits, and then for the rest of the 12, that would just be the actual value in the immediate field, which would be instruction EX31 down to 20. So I think that should do it. Yeah. So there's a sine extend. Nice and easy. Now with MIPS, there was a zero extend option too. But in RISC-V, there's no zero extend. It's only sine extend. Yes?
Will this be posted on Blackboard?
Yes, yeah, I can put, the lecture will be on YouTube, and I'll put this document on Dropbox, on Moodle. Okay, B, write a system Verilog snippet to implement the block that produces the GPIO out signal. So this is the way that you're going to get your 7-segment displays to display the number that you've converted. It's going to work off of this, it's going to work off the GPIO in, and I just realized that I did forget something here. So the GPIO in goes into a register, and the output of that register goes into the mux. Now the only input to that register is the input. There's no clock, there's no reset. And that's okay, because clock and reset are usually not shown because every register has that. However, it's also missing the enable input. Now that's important because if we don't have an enable input, you assume that the registers are always enabled, which means that basically all they do is delay the input by 1 cycle. The problem is that I'm sorry, I'm looking at the wrong one actually. Sorry, GPIO, yeah, that's this one. This does have an enable. Sorry, GPIO write enable is the enable for that. Yeah, sorry. Yeah, so we do have an enable, and so it's only going to update this register when it's enabled, right? And the value that we're putting in is from read data 1. And the reason for that is because the CSSRW instruction that outputs the GPIO value uses RS1 as its source register, which is why we've connected it to read data 1. Read data 1 corresponds to the contents of the RS1 register from the instruction, right, from the machine instruction. So how do we implement the GPIO out? We're basically just writing a register, right? That comes like pretty much from the slides when I showed you how to build a basic register. So you can just say always _FF at pos_edge clock, assuming that's what our clock is called. And then we can just say if GPIO _write enable, then GPIO _out gets with a blocking assignment. It gets whatever this signal is called. I don't have a name on it, so I'm just going to call it read data 1 _ex. Notice that the write enable is not in the sensitivity list. So the way this works is whenever you've got a rising edge of the clock, the enable state at that moment in time is checked, right? And if it's enabled, then you will capture read data 1 EX and move it into GPIO write. As long as the write enable is 0, then it'll just the GPIO out won't change. The reason for that, if you think of this as in terms of your program, you're only writing that register for 1 cycle out of 4,096 cycles. Assuming that you write your program, you only write the GPIO after you do your conversion, right? So you go through all the instructions required to convert binary to base 10 and put each digit inside of a register, any register you want. And then when you're done, you take the contents of that register and you kick it out to GPIO out. And so that should comprise 1 instruction out of 4,096 cycles, right? Because that's your instruction memory. So for 4,095 cycles, that guy's going to be disabled, meaning that it's just going to retain whatever the last output. And that's important because the 7-segment decoders that you guys wrote earlier is combinational logic. So you have to have something to continuously drive those things with a value that you want to display, right? Because they won't remember, right? They're just combinational. Okay, part C is in the following table. Mark the stage holding each of the instructions listed in the first 4 rows. Use the following abbreviations. Fetch is F, decode, execute memory E, write back W. So it's F, E, W are your 3 stages. Assume the instructions appear consecutively and the first instruction is fetched in cycle 0. Give the state of each of the control signals shown in the last 5 rows in each of the 6 cycles. Use U to denote an unknown value and X for don't care. So in cycle 0, we're going to be fetching the first instruction. And yeah, and then in cycle 1, we're going to be fetching the next instruction. In cycle 2, we're going to be fetching the next instruction. And then in cycle 3, we'll be fetching the next instruction, right? Which means that in cycle 1, we'll be executing the first instruction, and in cycle 2, we'll be executing the second instruction. No, sorry. I screwed that up. Fetching in cycle 0, fetching in cycle 1, executing. Right. In cycle 2, we're going to be fetching the mult, and we'll be executing the OR, and we'll be writing back the LUI. Right? And then in cycle 3, the LUI will have been completed, and we'll be writing back the OR, we'll be executing the mult. Sorry, I went in a different order that time. So, yeah, so fetching the LUI, fetching the OR, fetching the mult, fetching the move from high, right? Also, by the way, move from high, that's from MIPS. I forgot to update that. But we'll just assume there's an instruction there, some other instruction. Okay, cycle 4 then, we'll have finished the OR, so we'll be writing back the mult, and we'll be executing the move from high, and we'll be fetching whatever instruction comes after move from high. Okay? Make sense?
What move from high you mean that to do?
Move from high in MIPS, the multiply and the divide instructions didn't actually write a register, the general purpose register. They wrote 2 special registers called high and low. And then you had to subsequently have a move from high and or move from low to take the high and low registers and copy them into a general purpose register.
So you just copy from one register to another?
Yeah. Yeah, but it's the high and low are special registers. They're not numbered registers. They're not like in the register file. So the RISC guys decided to not do it that way, and that's why we have the multiply high instruction instead. The multiply, and then with the divide, there must be, with the divide, in the case of divide, when you did a divide in MIPS, it would put the quotient in high and the remainder in low. I think in RISC 5, there's probably just a remainder instruction, right? Okay. All right, so.
Can you please separate the windows so in one part we would see the diagram and
Oh, sure. Yeah, I can zoom out. I can zoom out here a bit. That's a good idea. Okay, hopefully that's not too small to read here.
there is a separator with something.
Maybe I can.
No separator, please.
Well, let's see. I'll just take that off and move that down for now. That'll be easy. There we go. Okay. Okay, so just a tad. Okay. Okay, so reg write. There's 2 ways you can approach this next part. We can fill in a column, for each instruction, right? Or for each cycle, I should say. Or you could just go horizontally. I think the easiest way is to go horizontally, because if you're determining whether reg write is asserted, all you have to ask is the instruction in the execute stage writing to a register? And so in cycle 0, well, we don't know what's in execute in cycle 0. In cycle 1, we've got the LUI, which does write. In cycle 2, we've got the ORI in execute. That does write a register. In cycle 3, now if this were MIPS, if this were MIPS, the multiply would not write a register, because as I mentioned, it wrote the high and low registers. But we'll just assume that since this is RISC 5, we'll just call that. We'll say that it does. The multiply does write a register, and then the move from high, we'll just assume that also writes a register. So reg write is actually high in cycles 1 through 4. Reg write back depends on whatever instruction is in the write back stage. So we don't know what instruction is in write back during cycle 0 or 1. In cycle 2, we've got the LUI in write back. So, yes?
Can you point to the diagram where the signal is?
Oh, the reg right, yes. Reg right is, the reg right EX is here, and then it goes into the register, and then the reg right WB is the signal between this register and the register file. Yeah, it's not marked on there, but that would be the delayed form. The delayed, it's reg right EX delayed by 1 cycle. In this case, reg right EX is always 1, so we can just fill in 1s for all the cycles, except for the first 2, because of the way that we have it pipelined. We don't know. There's no way for us to know what reg right back was the value of that in the first 2 cycles, because it took 2 cycles to get the first instruction here into that stage. Bless you. Okay, enable high and low. I'll just skip that one. That's MIPS specific. Reg select. Reg select. Where is, right here. Reg select is controlling what gets written back to the register file, but there's 2 versions of that, right? Yeah, there's a reg select EX and a reg select write back. We're looking at EX version, so we have to look at whatever instruction is in the execute stage. We don't know what instruction is in execute in cycle 0. In cycle 1, it's LUI. Okay, LUI. So LUI would be taking this instruction EX 31 down to 12 concatenated with 12 zeros, right? And so that's 1. Yeah, that's option 1. So, but it's 2 bits, so 2'B01. Okay, and then cycle 2 would be the same, yeah, because it's OR I. So OR I uses an immediate. Oh no, actually, wait a minute. No, that's not true, because OR I uses an immediate, but it's not the upper immediate. OR I actually is going to be the output of the ALU. I mean, you route. So with OR I, there is an immediate involved, but the immediate comes in through this mux and goes in the ALU. So the OR I would actually, in terms of what you actually write back, see, the LUI is just the immediate, but the OR I is you take the immediate and you do something to it. So that's why we have to select the ALU output in that case, which would be a 2. So 2'B2, 2'B10. Let's see, cycle 3 is the mult. And now again, if this were MIPS, this would be a don't care, because like I said, because of the way that it handles the multiply. But in RISC-V, the reg select for the mult would be ALU result, right, which would be 2. And cycle 4, let's move from high, and I don't know. I don't know what that one is, actually. We'll just skip that one because we don't have the hardware for that. Okay, reg select write back is pretty easy. We could just, instead of looking at what instructions write back, we can just take the value of the row above and shift it, phase shift it. So I'm just going to do that. I'm just going to take whatever was in above it and move it over by 1. So question mark moves over, 1 moves over, 2 moves over, 2 moves over, right? Because that's what the register does. And then ALU source, EX. Don't know what it is in cycle 0. In cycle 1, it's LUI. Well, LUI, though, in this case, see, the LUI is bypassing the ALU entirely, because with the LUI, we use this multiplexer to basically ignore what comes out of the ALU, right? So if I'm not using the output of the ALU, I don't care what the ALU is doing, because whatever it produces is not relevant for the instruction, and it will not be routed through this muck, so it won't go anywhere. It won't affect anything. So I'm just going to say don't care for that one. So don't care would be it's 1 bit, and it would be a X. Okay, cycle 2 OR I. Now this is OR I is an execute here. So execute is OR I, and the ALU source would require us to deal with that OR I, which means we have to ignore what's coming out of the second output on the register file and take the Sine extended immediate, and so it would be 1. And then cycle 3, we've got a multiply, so the ALU source would be 0 there, because for a multiply, we actually, we don't use an immediate, we use the read data 1 and 2, so ALU source should be 0 for that. And then in cycle 4, let's see, move from high, yeah, we don't know. I'll just say, sorry. Well, actually, move from high, again, if this were MIPS, the ALU source would be a don't care for that one. It would be kind of like a load up or immediate in RISC-V. But I'll just ignore that. Yeah, when I redid this whole diagram for this question, but I forgot that we had this MIPS specific instruction. It's one of the rare differences between RISC-V and MIPS. Okay, I'm going to go ahead and move this stuff back up again, just so I don't screw this up. Okay. Okay, in the following table, I forgot to move that up too. Okay. Question 5. What changes in the CPU design in question 1, and that should be 4 in this case, would allow the CPU to execute the SLLV instruction, where the SLLV instruction behaves as shown below. Shifts the register value left by the value in the second register and places the result in the third register. Zeros are shifted in. Well, in this case, this instruction is already built in to RISC-V. So this SLLV would stand for shift left logical variable. And so the idea with that was, in MIPS, the shift amount in a regular shift instruction was part of the instruction. It was a constant, or an immediate, right? Well, it was actually both, constant and an immediate, right? Whereas in RISC-V, they dropped that. They dropped the entire shift amount field, right? Did they? Yeah, there's no shift amount field in RISC-V. They got rid of it. So we don't have to do anything in this case. So that was a bad example. But the answer, yeah, so it says, you take the regs in T, you shift it by the regs in S, where S is essentially reads or register source 1 and T is register source 2. But anyway, in this case, nothing. But let's come out with another question here that makes more sense for RISC-V. Yes?
What do you mean by zeros are shifted in?
Oh, right. When you shift left, so when you shift left, the values on the left the bits on the left get shifted out. All right, they disappear. And then the values that you shift in on the right are zeros, right? Because it doesn't make it, there's really no other option for, unless you rotate, unless you get the values that you're shifting off the left and put them in the right. Some processors have a rotate instruction. I don't think I've ever actually needed a rotate. Maybe I just don't remember.
It can be useful for special purpose register for encoding when you have those ciphertext. Yeah, that's right. Probably, yeah, for stuff like encryption and maybe CRC checking, error detection. Yeah. Okay. So what else could we add to this architecture? The point of this is that you can add data paths to implement other behaviors. So, for example, and one of the neat things here is, let's see. So load upper immediate, for instance, right? I mentioned that doesn't use the ALU because, at least in this design, it doesn't. So you've got the immediate comes in. Actually, not the immediate 12, but the immediate 20, right? This is a 20. I just want to point that out. This is a 20-bit immediate, and this is a 12-bit. Load upper immediate uses the 20-bit immediate, and like an OR I, for instance, we use the 12-bit, right?
But the ALU is not doing anything. So is there anything the ALU could be doing? I mean, when we do a load up or immediate, well, maybe we could take. Well, I was going to say we could take one of the registers, and add it or something. But the problem is the load up or immediate doesn't have any register, right? Because that 20-bit immediate blows away all the RS1 and RS2. So.
Maybe we could combine lower upper immediate and side extend.
Yeah, you could. I'm not sure how useful that would be, though. Normally, the way I ask about like doing a load instruction combined with an increment, which would be something useful, like if you're walking through an array, but we don't have load instructions here, so that doesn't work. Let's see. How about the rotate that we just mentioned? So the ALU. See, the ALU, we'd have to implement that into the ALU, though. It would be more than just adding data pass. I don't think there's any way that we could do that. Let's think here. What else could we add? We could add an instruction that, let's see, we could, I don't know, I'll have to think about that. I can't think of anything right off the top of my head. I can't think of a good one for this because we're so limited. We don't have that much in here to work with. How about taking, I have an idea. How about this? What if we added a data path, if we took the program counter, right? We could implement an instruction that takes the program counter and writes into the register file, like does a link, without actually branching or jumping, just writes the program counter. So for that, all we'd have to do is create a mux or write, we could take the program counter and we could connect it to this mux. In fact, we have an open slot on that mux because there's actually 4 inputs. We only use 3 of them. So we could take the PC and connect it there, and then which would cost us very little. We just have to pay for that wire going there. And then we just have to add a line in our control unit that detects that instruction and changes reg select appropriately to 4, right? So that's a good one, right? We could have an instruction called write PC. Takes the PC and writes it to this destination. That would be super easy, super cheap, almost free to do that.
So there would be 2 wires, one from PC to the reg cell right back, and one from control unit to the.
Well, no, we already have 2 wires from the control unit, though. Reg select is 2 wires. So all we're doing is using another encoding, right? Because normally with this CPU, reg select would never be 1-1, right? Because we don't have the 4th input on that mux. But now, if we add our write PC instruction, we can simply set that to 1-1 and we perform that instruction, write the program counter to the destination. Okay. Okay. Write a sequence of 2 RISC instructions that would trigger the register file bypass. So this, I didn't talk about this a lot because we gave you the register file code, but I did cover it when I described what was going on in there because I want to make sure you guys understand how the code that we provide works. The register file bypass is happening whenever you, let's see, do we have that come up here? Or, yes, right here, as a matter of fact. So here's a sequence of instructions, load up or immediate to. By the way, why is there a 0 there? I just noticed that. Register 0? Yeah, that's superfluous. Okay, so we load 0, do a load up or immediate, which is, I mean, that's kind of pointless to do that. That would just zero out the register. I guess, well, it's one way, it's a legitimate way to zero out a register. But yeah, we write register 2, right? And the next instruction reads register 2, right? So when the load up or immediate is in write back, which happens in cycle 2, that next instruction, or I, is in execute. which means that we are writing register 2 and simultaneously reading register 2 in cycle 2. So that would activate that bypass. If you didn't have that by bypass, it's that special code in the register file that enables this to happen. Because if you just wrote a regular RAM, a synchronous RAM, then these two instructions would cause a problem, because the OR would be seeing the old value of register 2, which is the state of register 2 prior to the LUI. Okay, so anyway, the answer to the question is really simple. We have it right here. Is these two instructions together would trigger the register bypass. I'll just stick those in there. Okay. There we go. Any questions about that? Makes sense? Okay, what would happen if the register file lacked write bypass? Well, that's what I just said. The OR I instruction would see the old value of register 2 prior to the LUI instruction. Okay. Okay, next question. Convert the behavior of the following Verilog module, it should be system Verilog, into a truth table. So we've got an if statement, an always block with an if statement, but ultimately this just creates a truth table. How many inputs do we have? The inputs are essentially just A. A is the only input. A is 3 bits, so this truth table would have 8 rows, 2 to the 3rd power rows, right? So we insert a table with 8 rows, and the input is A, and the output is Y. And so I'll just do 2 columns. I could do, yeah, okay. So we have A and Y, and so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then we need one more for table layout, insert below, there we go, and 1, 1, 1. Okay, and then center this guy. Okay, so if A is 0, 0, 0, oh, this is a good question, yeah, because you have to follow the control flow through here. So if basically if A2 is 1, then Y is going to be 1, 1. So I can take all 4 rows that correspond to that. So there are 4 rows. These bottom 4 rows are going to correspond to this condition, right? So I can pretty much just say 1, 1, 1, 1, 1, 1, 1, 1 there, right? And then if A bit 1, which I have 2 rows for that, then Y is going to be 0, 1. That would be this clause, right? And then the last is the default, right? If nothing matches. So in this case, I'm just going to copy A, put that into Y. So not the whole A, just bits 1 down to 0. The rightmost 2 bits of A, which is going to be 0, 0, 0, 1. There we go. All right. Question 8, write a system Verilog module named minority. It receives 3 1-bit inputs A, B, and C. It produces a 1-bit output Y that is true if at least 2 of the inputs are false. So module minority, input logic A, B, C, output logic Y, right? End module. And then produces a 1-bit output Y that's true if at least 2 of the inputs are false. Well, if the two of the inputs are false. Okay, so I could do like a big if then else here.
We can combine them as not instructions. So for example, take and of not A, not B, and not C, and then one more word.
Well, but if at least 2 of the inputs are false, that would basically mean that 100010001 or 000, right? Right? Yeah, so I could say if, well, is there a way I could do a reduction, right? So I can have a logic, say so there's 3 bits, that's going to give me a number up to 3, so 1 down to 0, sum of bits, and I can say assign sum of bits to be the reduction. Do we have an add reduction? Oh, I don't remember if we have an add reduction, do we? I'm thinking of OpenMP. I'm not thinking of Verilog. Yeah, we don't have an add reduction. So that's not going to work. Sorry, scratch that. What are the reductions? We have or, yeah, and just logical operations, right? Yeah, so that's not going to work. Well, I can just, the easiest way to do it is to just say assign y equals that when
It can be not A and not B, or not B and not C, or not A and not C. Just go through all of them.
okay, yeah, that's a good one. So just minimize it. Okay, so not A and not B, or not, would you say not
Not A and not C.
not A and not C? That's right. All right, and
Not B and not C.
and these are ands, not ors, right? Yeah, not B and not C.
And you have one extra and there.
Yes.
No, the rightmost couple. You have not and not B.
Oh, you're right. Yeah. Yeah, and it's or, right? Yeah. Okay. Gotcha. Yep. Yep, that'll do it. Yeah. So basically, that's checking to see if at least 2 are. That's just a. Yeah. That's pretty much just a translation of what the text says, right? Yeah. Okay. Good. Thank you. Write a self-checking test bench for this module. Ooh. Okay. So for this, I'll just say module dot with no inputs outputs, and module. First thing we have to do is we have to instance the minority called dot. Okay, and then I have to connect A to A, B to B, comma, dot C to C, comma, and Y to Y. And this will be, yeah. Right, and then I just need initial, begin, end, and then I just say set A to be 0, B to be 0, C to be 0. Now I'm putting these all in one line. Yes. Well, actually, you know what? It'd be better to do it this way. Let's say A, comma B, comma C. Yeah, there we go. Assigned 0, 0, 0. There we go. Yep.
Can we have a 3-bit input and just put each bit to the inputs and then just increment it as a counter?
Yeah, sure. Yeah, we could have a counter in there. Yeah, the problem though is that we need to have the expected. We have to figure out where to get the expected output, which of course we could just use the same logic as in the dot, but then it's not a good test because we're using basically the same implementation to test the design. So I'm just going to go ahead and I'll just do it just a straightforward way where I'll set the inputs, I'll put the delay in, and then I'll say if y doesn't equal, in this case should be 1, right, because it's 0, 0, 0, right, then display error, right, and then I would put this in 7 more times. 1, 2, 3, 4, 7. And then I need to put in my counting sequence. So it would be 1, 2, 3, 4, 5, 6, 7, and then for y, it's pretty much just going to be 1, 1, 1. That would be a 0, right? Yep, because there's only one false there, right? 1, 0, 0, and 0. There you go. So in this case, you would compile the minority, you compile this, and you'd simulate this as the top level. Yes?
I think you forgot why before the dot in the declaration of the connectivity of that, and also you forgot to declare the
Oh, you're right, I did. Yeah, thank you.
A, B, C, and Y.
Ah, yes, that's also a good point. Thank you. Yep. Logic A, B, C, Y. There we go. Now I have a local version of A, B, C, Y in the dot. Okay, thank you. Good, good. Write a system Verilog module named majority. It receives 3 1-bit inputs, X, Y, and Z. It produces a 1-bit output A. That's true if at least 2 of the inputs are true. This module must instantiate the minority module and use it to compute its output. Okay. Okay, so basically, interesting.
It just take Y and inverse it.
Yeah, oh yeah, there you go. Yep, that's it. So module majority, this inputs logic A, B, C, output logic Y, and module. And yeah, I think that's a good way to do it. So we'll just create a minority inside of here and call it, I don't know, foo. And then pass it the inverted, the complemented A, B, and C. So A is not A. B is not B. And C is not C. And Y is Y. There we go. All right. Makes sense? Okay. What's the purpose of the sensitivity list in a system Verilog always statement? Activates the statement when any of the signals in the sensitivity list change. State, value, whatever. Okay? Blocking assignments update the assigned values immediately, while non-blocking assignments update the assigned values after all other actions associated with the current event have completed. How many clock cycles of delay will the code below impose between input in value and output D? So this is a always FF pause edge clock. So in val, A gets in val, and then B gets A. But because this is a blocking, what will happen is that A and inval are effectively the same signal in this case, in this context. So
First cycle
on
B got inval.
yeah, so then B, and the same thing happens here between B and C. So there's a 1 cycle delay from inval to B, and there's going to be a 1 cycle additional cycle of delay to D, right? So even though there's 4 statements here, this will be a 2 cycle delay. This will be a 2 cycle shift register, basically, right? So how many cycles of delay will the code below impose? 2. Okay. Assume the CPU can execute the following instructions: add, subtract, BEQ, LW, SW. For which of these instructions is the reg file signal not asserted? Okay, so we didn't talk about load word, store word. Oh no, actually we did talk about that when we were going over the RISC stuff. We're not implementing those in our hardware, and we haven't done the branch equal yet. But I think you can pretty much imagine that how you'd have to approach this. It's pretty much the question is which of these instructions write a register or write a general purpose register, a numbered register. So that would be add, subtract, and load, right? The branch would not write a register, I mean, aside from the program counter, but that's not, reg write doesn't control the program counter. And store word, that doesn't write a register, that writes in memory. Yes?
Why reg write? You meant reg write execute, right? Not reg write. Reg write execute.
Yes, yeah, that's right. That's right, that's a good point. Yeah. Yeah. Actually, well, yeah, that's right. I mean, what I meant was in the control unit, like when you write the control unit, you have a reg write associated with each of these instructions, so what would that value be? But yeah, it would be reg write in our design. Reg write EX rather. Well, actually, if you have a separate module for your control unit, it may not be called reg write EX in the control unit, but it's called that in the CPU. Okay, fill in the table below fill in the table for the module below. Use question mark for unknown values. So this thing is another delay type thing. Basically, it takes, oh wow, these are out of order. A goes into B delay 1, B delay 1 goes into B delay 2, B delay 2 goes into B. Okay, but that's okay. It does. These are, remember that these are non-blocking. Doesn't matter what order you write these in. So it's okay they're out of order. That's not a problem. So basically, B delay, let's see, A gets B delay 1. So I don't know what it is in the first cycle, but B delay 1 is the delayed form of A. So all I have to do is copy the A column, but it has to be shifted by one cycle, right? So now remember before, hopefully this isn't, I don't confuse you here. When I did something similar before, I had the cycles going across the columns of the table, right? And now the cycles are going down the rows of the table. But it's the same idea. I just kind of transpose the way I represent the table, right? In ModelSim, you can actually have ModelSim print out all of the things in a listing view as opposed to a signal view, in which case the ModelSim will actually use a table like this, where time ticks down. But in the normal waveform view, it goes horizontally from left to right. So the purpose of this is to just get you used to the idea that you can represent this either way. But B delay 2 is just, again, is 2 cycles delayed. So I'm just going to delay B delay 1. So 0, 1, 0. And then B is another cycle of delay. So it's a 1 cycle delay of B delay 2. So pretty much, yeah. So all I did was I took, this is just the copy of this, but moved down, right? And then I did the same thing. Now in this case, ModelSim is going to show a red line for the unknowns. Yeah, but it's okay because that red line will eventually become 0, but not until cycle 3. Okay, all right, number 13, assume the module below. How many total bits comprise the inputs to module AAA? Anyone know that? Yes?
2 bits comprise the inputs.
2 bits, yep, that's.
And the outputs is just 1.
That's right. All right, fill in the missing values for the test vectors for testing module AAA. So if A is 0 and B is 0, then that would be like saying, oh, that, actually, you know what, is it? I always screw this up if it's tilde or
In Verilog?
in Verilog.
In Verilog it's tilde.
I always screw that. I think it's not tilde. Charles pointed this out last semester that the tilde, actually, I got that from MATLAB. But in Verilog, there is no tilde. I think it's just, I think a complement, whether it's a logical or a bitwise complement, they use exclamation point, I believe. But I keep making that same mistake. I keep putting the tildes in there to negate, but that's not the right syntax.
I saw tilde in our Verilog. Well, again, we can Google for that.
Yeah, we'd have to Google it. I don't know.
Google says that tilde is an operator.
Oh, okay. Maybe I was right about that then. Okay.
I have a question for the A.
Yes.
Like it comprises of 2 parts. How many total bits the inputs is 2 and how many total bits the outputs is 1, right?
Yep.
So why the answer is 2 for A?
Yeah, inputs are 2. I forgot the answer, the output part. You're right.
Yeah, Google says tilde making the exclamation marker interchangeable.
Oh, okay. Sorry. So I was good then. Okay, tilde. Tilde's good. All right, good. Okay, so so this is basically 1 and 0, so that's going to be a 0, right? Now, let's see. This one is a little ambiguous because I know my expected output has to be 1, so I have to work backwards. So for the output to be 1, if B were 0, then A would have to be, I'm sorry, if B were 1, A would have to be 0, right? And then, let's see, 0, 0, 0, 1, I guess this would be 1, 0 most likely, which would give you a 0 output. And it doesn't matter, right? I could change those two, right? Yeah. So the last two rows, yeah, that's right. But there's 1 in either, yeah, so it's good.
It
Yeah.
can be 1s, it can be 0s.
Right.
The last two rows.
Yep. But I have my rows are 0, 0, 0, 1, 1, 0, and 1, 1. So I got all the 4 inputs. Okay, assume the following module which instantiates the module above, module BBB, AAA, my AAA. Now I take, okay, this question is just asinine. Yeah, I shouldn't have asked this one. Okay, so basically it's essentially telling you to do the same thing, except now it's needlessly renaming the signals through the hierarchy. Okay, so C is now A, A is now B, B is now, I don't. Yeah. Anyway, you have to do the translation essentially. But the good news is I think the table, the way I have the table set up is it's A. You can just pretend that's A and that's B, right? And then expected B would be the C. Yeah. So 0, 1, 0, 0. So that's not too bad. The table makes it easy. Describe any problems with the code below.
Your instancing always comes twice. Alright, that's really confusing.
Yeah, and also this should be comb, by the way. This is the old Verilog syntax. I forgot to update this. Okay, so we use always comb instead of always at star. Okay, so what's the issue then? You can have, we can have 2 always statements, so that's okay. But what's the problem?
You could do it, there's a lot, it's a logic. No, it's not a logic error. It's just really weird how you would have it, because you can just do it. It's just much simpler if you just, the logic for output, you need that. Logic
Yes.
for output, you need that. But the weird part is like, you can do it so much easier if you just say if A, then B, because it's a truth, it's just a single bit. It's just a truth value.
Go
I
ahead.
think it will make it flipping a 0, 1, 0, 1 because, okay, let's say B is 0. We go always come, I see. It just, if we had 0 there instead of 8.
No, there's yes. Yes, that's the problem. B is actually double driven here, and it's guaranteed to be in conflict because the conditions, so if A, regardless of if A is 0 or 1, we're going to be, what's going to happen is, there's no else here either. So one of the problems, there's no else on those, so those always will end up being a latch, first of all, right? That's one problem. We should have had an else condition for these guys, right? But the other problem is even then, even with the latch, they're still both driving B, right? And so what'll happen is, now you might say, well, wait a second though, like, if A is 1, this guy activates. If A is 0, this guy activates. But this first guy will still be driving B even if A is 0, right? Because it's a latch, right? It's still going to be driving the memory, the remembered value of A, right? Or of B, rather, in this case, right? So
the problem is that the B is double driven.
Yeah, B is double driven. Yeah, that's what I was going for anyway. B is double driven. Okay? Okay, next.
I have a question.
Yes?
So if we replace the first question always come with else, that should be fine then. Second always come, replace with
Yeah,
else.
sure. Yeah. Yeah, if you'd have to take out the second always com, but yeah, that's right. You could merge them into one always com. Yeah. Okay. Number 15, describe the process by which a user-entered HDL design is converted to a form that may be loaded onto an FPGA. This is just kind of a short answer question. The process is you synthesize the code, and then you place and route it, and then you generate a bit stream, and then you load the bit stream on the FPGA, right? So basically, you essentially compile it. But synthesize, place and route, generate bit stream, program FPGA. And you guys have all done this, right? So you know the process. Okay, 16, describe the process by which an FPGA is programmed. Bits are shifted serially into the FPGA to configure all LUTs, RAMs, etc. Pretty much, yep. Okay, and that's the last question I've got. So that timing worked out well. Yes?
Could we have some parallel ports? So instead of serial bit by bit programming, we might have 8-bit flash.
Yeah, I think it actually does work that way. I think they have they divide up the shift registers into parallel shift registers to load it faster. But the point of that is that when you configure an FPGA, even with that, it takes on the order of seconds to program even a small FPGA. And so this basically means that you can't time division multiplex an FPGA practically. You can't say, oh, I've got a design that doesn't fit on the FPGA, so I'll time multiplex it. I'll do this function, reconfigure it, do the next function, reconfigure it, go back to the first function, etc. It's not practical. It's too slow. It's too slow. So there's no. Now you can partially program some FPGAs, and you can have one part of the FPGA still running while you reconfigure another part. But in practice, that's very tricky.
You can just connect external pins of the FPGA to some external module and just trigger those pins and have an external multiplexer and just connect it to different physical modules to have
Oh, physical, but you need more than one FPGA though, right?
It could be FPGAs, but for example, if you need simultaneously use ADC and DAC, like a digital turn-up, you can have just separate modules which are not FPGAs, but just some hardware which
Sure.
It serves its purpose. And you can add multiplexer and just have external GPO pin which selects which part you want to use.
Yeah, you could do that. Yep. Yes.
Would you say this represents our exam well, or should we go back to the slides?
It's similar. It's pretty similar, but you might want to review the slides. It's multiple choice, so the format is different too. So the form you have to be real careful when you select those.
Okay.
Some of the answers are very similar.
Okay.
But I believe there should be something like typing down or something like this, so not necessarily.
Yeah, there is, but I haven't figured out a practical way to implement that. I mean, the Moodle supports it, but like if you type in code, like there's different ways to write code, and we could grade it manually. That's one option. But I think I might do that for the final, but we'll see how it works out with the midterm. It's hopefully no one has any big problems with it. Just be careful, because it's only 15 questions, so if you miss one, it's they have a 1/15 of the grade. Okay. Yes.
Say if you were to ask the question about the diagram, the CPU diagram, and would you ask this like the same way you asked this in the quizzes, or would you like to?
Yes. Yeah. I might say something like, fill in the control signals. I think I have a couple. Yeah, I had a quiz and question. Yeah, or questions in the quiz like that. Yeah, yeah. I think I do have some like that. I don't even. I've already forgotten what I put on there, but I'm pretty sure I do have questions like that. Yeah. Okay.
Thank you.
All right. Thank you.